W in R to the n such that the initial ideal of I contains no monomial. Right? I mean, that's exactly for a hypersurface minimum for a single polynomial. Minimum is attained twice means that the initial form is not a monomial. Right? So there is a tie among the initial terms. So therefore, the initial ideal contains no monomial if none of the initial forms is a monomial, and that's exactly equivalent to the definition. So that's an easy lemma. Okay, so here is a first theorem whose proof I will actually give. So the tropical variety of a classical ideal is the support of a polyhedral complex in Rn, and the second part is if the value group is trivial. So if the field of definition of I has trivial valuation, or if there are no t's in the coefficients of the polynomials, then this polyhedral complex is in fact a fan. So this parenthesis I need. So when I say tau of I is a polyhedral complex, so tau of I is a subset of R to the n, I will mean there exists a polyhedral complex that has this support. It's not unique. Same if I say, the tropical variety is a fan, what I mean is it's a subset of R to the n that has the structure of a fan. Yes?
Does the operation only satisfy some kind of things for the homology?
It satisfies some things. These are certainly closed sets, but it's a little bit delicate to talk about Zariski topology here. So the short answer is no. We can end the discussion by saying no, but some things are still true. Let me actually prove this theorem. So I'd like to actually prove this theorem. So we worked hard this morning, so now we're going to reap the fruits. Now we derived the Grobner complex, and now it's easy to derive this theorem. So first of all, I like to argue we can replace I by its homogenization. So by the homogeneous ideal in one variable more, x0, x1, up to xn. Because, why can we do that? Well, I claim that the following relationship holds. The tropical variety of I is simply the tropical variety of j intersected with the hyperplane where the new coordinate is 0. Okay, so I'm embedding Rn into Rn plus 1 by putting a 0 in the first coordinate, and then I can recover, the tropical variety of I by just from the tropical variety of j. So without loss of generality, I can homogenize my equations, and if I can prove, so if this is a polyhedral complex or fan, if I intersect it with the hyperplane to the origin, the result will be a polyhedral complex or fan. So therefore, it's enough to look at the case of a homogeneous ideal. Now, for a homogeneous ideal, the Grobner complex exists. That was the main theorem this morning. So the Grobner complex, and that's a non-trivial theorem, actually. The Grobner complex exists. We called it G of j. So let's call it G of j exists, and it is a fan. And it is a fan if the field of definition has trivial value group? Well, but then tau of j, so by definition of Grobner complex, on each relatively open cell of the Grobner complex, the initial ideal is constant, right? So therefore, tau of j is a union of closed cells. In G of j. And that ends the proof. So why is it closed? Well, suppose, some cell has the property that this ideal contains an homonomial. Then every face of it, that's will even, if you're passing to a face, it will in particular also have this property. It will be even bigger, the initial terms. So therefore, the set of cells in the Grobner complex that lie in tau of I will be closed downwards. So it's a union of closed cells, and so therefore it's a complex, right? So I have a polyhedral subdivision of R to the n, and I take a union of closed cells, and then by definition, that's a polyhedral complex. And if the thing I started with was a fan, I get a fan. So this structure of the tropical variety follows immediately from the existence of the Grobner complex. Okay, so now we can ask the following question. Suppose I have any ideal. So given any ideal I, any system of polynomial equations, how to compute the tropical variety? How do you calculate the tropical variety of an ideal? Well, there are two answers, depending whether at Kias you're in the division of computational science or whether you're in the division of pure math. If you're in computational science, we know the answer, right? The answer is you run GFAN, right? You let I be any system of multivariate polynomials whatsoever. You take the laptop that the gentleman provided, you plug it in, you type your equations into GFAN, you hit the button, and out comes the tropical variety. So that's one answer, right? So GFAN will calculate for you the tropical variety for any polynomial ideal. Now that's a bit of an unsatisfactory answer if you're a pure mathematician. You like to have a more conceptual description of the tropical variety, and we're going to come to that in a second. Okay, so second answer gets derived as follows. Let's note that the valuation defines a map. I'll also denote val from the algebraic torus k star to the n to R to the n. So simply by applying the valuation coordinate-wise, right? So the valuation is a map from k star to R. If I apply it, coordinate-wise, I get a map from the n-dimensional algebraic torus to R to the n. Now, if I have an ideal, for instance here or in the law polynomial ring, I'm going to, for an ideal I, let V of I be its variety in the torus. Okay, so I'm only taking those zeros, those solutions to the equations, all of whose coordinates are non-zero. Then we have the following fundamental theorem. So this theorem is so fundamental that we're going to make it yellow and red. Okay, so here's the statement of the fundamental theorem. It says, if you apply the valuation to the classical variety in the torus, okay, you're going to get a subset of R to the n, and this subset is equal to to the tropical variety. Well, not quite true. It's almost true. You have to intersect, with all the rational points. You have to actually intersect with the value group. Okay, so the image of the valuation. Okay, so you take, so modulo this fine print, the tropical variety is the image of the classical variety under the coordinate-wise valuation map. And this you need, right, because I define this over the real numbers, but for some fields we only get rational coordinates in the valuation. And that's why Thomas Markvik, there was our last example, we had this field with real exponents, then you don't need this, right? So if this is all of r to the n, that's a technicality. The main point is this is equal to that. The tropical variety is the image of the classical variety under the value map. Now, moreover, there's even a stronger statement. Moreover, if V of I is irreducible, if I have an irreducible subvariety of the torus, then every fiber of the map, so there's a map from V of I to tau of I, so that map always exists, and the main point of this fundamental theorem is that the map is onto, but this map is not just onto, it's really onto. It has lots of stuff in the fiber, right? To be really onto means that every fiber is big. There are lots of things that map to it. So if it's irreducible, then every fiber is Zariski dense in the variety. So this is a very strong form. This just says it's not only onto, but there's lots and lots of things in the fiber. Okay? So that says that's the fundamental theorem. And we're going to see some examples and uses of this in the exercises. What I'm going to do now is I'm going to prove there's an easy direction and a hard direction. And I'm going to prove the easy direction, and I'm referring you to the notes for the hard direction. So the hard direction is actually proved in the notes. But I'm just going to prove the easy direction for you.
Your note seems to contain many typos. Are you soliciting correction?
Yes, I would love to. I mean, the notes are terrible, So you Xerox them for the participants, or some people. Some people.
I can distribute them tomorrow.
No, don't. Delete them. They're terrible, So yes, we would love to have typos and mistakes, When I first announced the lecture, I had hoped that we had made much progress, but we really didn't work on them at all in the last couple of months. So they're in very, very bad shape, but I still would appreciate, comments. So yes, please. The best is by email. So if you could say, each and one of you, each person, please find 5 typos. Okay? So yes, absolutely. Please find mistakes, typos, comments. But the disclaimer is, we haven't put any effort into this yet, and they're pretty bad shape. But the proof is sort of there. The proof of the fundamental theorem is there. Okay, so let me prove the easy direction. So the easy direction is the left-hand side contained in the right-hand side. So I want to show that this map actually exists. Right? So I want to show that the valuations of the tropical variety, of the classical variety, lie inside the tropical variety. So I want to show, that this map exists. That's the easy direction. So let's prove the easy direction. Okay, so suppose something is in the left-hand side. So W is in the image of the classical variety under the valuation map. Well, then let's pick any pre-image. So there exists a U in the classical variety with value of U equals W. We must show, So this W is on the left-hand side. What we want to show is that for every polynomial in the ideal I, W is in the tropical hypersurface of F. And I'm going to write capital F for the corresponding tropical polynomial. So I want to show, for every polynomial F in the ideal, the leading form is not a monomial. Okay, that's what I want to show. Well, let's look at the expansion of this polynomial. So let's write f of x is the sum over some alpha c alpha x to the alpha. And let me write capital F for its tropicalization, tropical sum. And then here we have the values of C alpha, tropical product. Let me call this actually Z, because I've used W already. F of Z, and then Z, tropical power alpha. But what do we know? Well, we know that F of U is equal to 0, right? U is in the variety of I, right? So since U is in the variety of I, F of U is 0. So therefore, this says the sum C alpha times U to the alpha is equal to 0. But what does that say? Well, remember all the coordinates of U are non-zero, so this means there must be a cancellation among lowest terms. There must be two indices, A1 and A2, such that, the valuation of this term, which is the value of C A1 plus A dot W. W is the value, yeah? So the valuation of this, the value of this is the dot product W dot A, right? Because W is the value of U. Okay, so that's the value of the A alpha term. This is equal to the value of some other term. That's A1, A2 dot W, and it's less or equal to all others. C A plus A dot W for all other A. And that's the only way, right? In order for this to be 0, in order for this expression to be 0, if you look at the valuations, right? These are all non-zero elements in the field, so they have a valuation. The lowest order must be attained at least twice. But what does that say? Well, that says, right, so the minimum is attained twice. Is attained twice in a tropical polynomial. Well, there it is, right? It's attained twice in when we plug in Z equals W. So sum over all A val CA times WA, but that says W is in the tropical hypersurface. And that proves the easy direction. So the easy direction is quite easy, right? So it really just follows from the definition, and we're not using anything. We don't use that the field is algebraically closed or anything. The converse is quite hard. And actually, it's quite delicate. There's several proofs in the literature, and there's a proof in the notes, but it took a while. There were some proofs in the first publications on this that had gaps. So it's a bit of a delicate argument to actually prove the converse, and I will not give it here. Right? So the converse says if you have any point in the tropical variety, you can lift it to a classical point in the classical variety that has that given valuation. And to carry this lifting out, to prove it is hard, but we're in kiosk computational science. So when this afternoon you download the singular library tropical.lib by Thomas Markvik, you can do the lifting. Right? So this singular code, you can specify any point in the tropical variety, and it's going to make a power series solution for you. It's kind of like a Hensel lifting, but it's sort of a delicate lifting. You have to know the valuation, and you have to make a point. But you can play with this using singular. Okay, so that's the fundamental theorem. Now there are a couple other theorems there's something we call the structure theorem. Let me state that. So the structure theorem for tropical varieties the structure theorem says the following. It says the dimension of the tropical variety equals the dimension of the classical variety. It's the first part, right? So the dimension of the polyhedral complex tau of I equals the dimension of the classical variety. I'm going to come to the second part. Now that's a remarkable theorem. If you ever taught or taken commutative algebra or algebraic geometry, you get to the definition of dimension. So at some point you have to teach the definition of dimension. That's not so easy to teach, actually, you know. I mean, there's the notion of Kroll dimension, you know, which has to do with chains of prime ideals, you know, so that's one definition of dimension. Another definition of dimension has to do with transcendence degrees, you know, or field extensions, right? And then there's another definition that has to do with the degree of the Hilbert polynomial in projective geometry. When you teach this, you have to prove that these are equivalent. And, you know, the dimension theory is not so easy to teach. Suppose you don't like any of those definitions of dimension. Here's another definition, right? I've given you a definition that you can use when you teach commutative algebra. I is an ideal in a polynomial ring, right? Take any polynomial, look at all points such that, you know, there's a tie among leading terms. That's a subset of R to the n. It's a union of linear pieces. Take that dimension. So if you want, you can use that as definition of dimension when you teach commutative algebra. Well, anyway, in a polynomial ring. Okay? And it's the same. So the second part is if I is a prime ideal. If I is a prime ideal, so if the variety is irreducible, it's even better. Then the tropical variety is a pure complex. Is pure and strongly connected. Okay, so what does this mean? Well, suppose you have a variety of dimension d in projective n space. So pure means that each maximal cell has the same dimension. So a pure complex means that each maximal polytope or polyhedron has the same dimension. Okay, it's a pure complex. Strongly connected is even better. Strongly connected means that the ridge graph is connected. So if you have two maximal cells, you have a maximal cell here of dimension d, and you have another maximal cell here of dimension d, there exists a sequence of paths of maximal faces, each which meet along codimension 1. Okay? So that's a polyhedral complex that's, you know, strongly connected. Now that's a very, very important algorithm that's key in the implementation of GFAN. Right? When GFAN runs and makes the tropical variety, it uses strong connectivity. It finds the first maximal cell, then it moves and finds a second. The graph is connected. It searches the ridge graph, and so we need, you know, this is crucial for the implementation in GFAN. Okay, that's the structure theorem. Let's do an example. So that's all. Are there any questions about the statement of either the fundamental theorem or the structure theorem? Somebody would like to volunteer to present it on Thursday. Yes. So we need somebody who has a sort of a background in commutative algebra a little bit. Anybody interested in reading the converse proof? No, but you have already another assignment, right? You have to answer all questions. So maybe I'll get back to you. But let's hold off. Let me find, you know. Do you guys really want this lady, you know, from Toronto to come in and take everything over? You know, all you guys and girls from Korea. Anybody out there who would like to read the proof of the converse and present it maybe? Okay, you can identify yourself over lunch, so maybe we'll find a suitable reward, So on Thursday we'll have a lecture on the converse. Hyungju will appoint somebody, but it should be somebody who knows a little bit about commutative algebra and local rings, that kind of thing. You need a bit of the technique.
Is a designated teaching assistant for this summer school.
Okay. On Thursday afternoon we'll hear about the converse. Okay. Any other? And you can help out, but we don't want to, we don't want to use you for everything. Okay. Then let's do examples. Okay, if there are no questions about the statement, if the statements are clear, let's do some examples. So here's an example. And let's do one example. Let's do this very, very slowly. So let's take f to be the 3 by 3 determinant. And now I'm going to take the general determinant, not the symmetric one. Okay? So f is a homogeneous polynomial of degree 3 in 6 variables, in 9 variables having 6 terms. A cubic polynomial in 9 variables having 6 terms. The variety, what's the variety? V of I is the variety of singular matrices. Singular 3 by 3 matrices, right? So the determinant vanishes if and only if the variety. But we're taking the variety in the torus. So these are singular 3 by 3 matrices whose 9 entries are non-zero scalars in K. Okay? Now then we have the tropicalization. Capital F is the tropical. The tropical 3 by 3 determinant, that's the value function in the assignment problem. Right? So we have the assignment problem that finds the best assignment of 3 jobs to 3 workers, and that's the tropical polynomial. Now, here's the tropical hypersurface. So these are all assignment instances that have a tie. The tropical variety is all those matrices where the minimum is attained twice. So these 3 by 3 matrices for which there's a tie in the assignment problem, for which the assignment problem has more than one optimal solution. Okay. Well, what's the dimension of this tropical variety? Well, we're in a 9-dimensional space. Hypersurface has dimension 8. It's irreducible, So this is an 8-dimensional polyhedral fan. A pure, strongly connected 8-dimensional polyhedral fan. Well, let's pick a point in this tropical hypersurface. So let me pick a concrete point. Let's pick a matrix. So here's an example of a tropically singular matrix. 1, 0, 4, 3, 1, 2, 0, 5, 0. So that matrix lies in this tropical hypersurface. The determinant is 2, and it's attained twice. Right? So we have this times this times this. Tropically is 2. This times this is 2, and that's the smallest value. So this is a matrix that lies in the tropical variety. Okay, so that's a tropically singular 3 by 3 matrix. So now I would like to do an in-class exercise. So this is something I do when I lecture. So in my daughter's school, this is called Do Now. Okay, this is a Do Now assignment. And since we're going to start, we started at 10 minutes after, we're going to go until 10 minutes after. So we have 19 minutes. And I'm going to speak for 1 more minute. So You have 18 minutes to do the do now exercise. Okay? And there's two parts to it. The first part is, well, do you really believe the fundamental theorem? Show me, right? So construct a singular matrix. So find a matrix U in the classical variety. So find a singular 3×3 matrix whose image under the valuation map is equal to W. Right? I mean, the fundamental theorem says the tropically singular 3×3 matrices are the image of the classical, singular 3×3 matrices under the coordinate-wise valuation. So can you find a 3×3 matrix U that's singular, whose entries are, and you can pick a field, I mean, if you like number theory, you can pick the p-adics, but let's see whether we can do this over the rational functions. Okay, so you're going to fill a 3×3 matrix with rational function entries such a way that the matrix is non-singular, and you get this valuation. That's the statement of the fundamental theorem, that you can do this, right? So that's part one. And part two is draw the tropical variety. Now that looks like it's very, very hard because it's an 8-dimensional fan. But this 8-dimensional fan has a very, very large linearity space. And you can mod out the linearity space to get a pointed fan. When you're there, you can draw a beach volleyball. You can intersect with the sphere, and you can pass to a polyhedral complex of 1 dimension lower, and then you can draw it. And now we only have 17 minutes left. So those are the two assignments, and I'd like you to think about them now. So make a matrix. And for the second one, I have a hint. So yesterday, I saw somebody here had this book called Algebraic Statistics. You have this book? Do you have it here? Oh, in the hotel? No? Okay. Well, we might have to. I have it on my laptop, but the answer is in the book. So maybe somebody can find the book. So the answer is in algebraic statistics for computational biology. Figure 3.5 on page 114. So maybe we can find it. But let's start with the first one.
Explain my thinking behind it. So.
Why don't you write it down? Let's write the answer, and then we can see whether it's true.
I'm thinking that. Is that even less? Yeah, nice.
Okay, well, let's wait 1 second. So let's first check that this has the correct valuations, right? So this has value 0, 2, 4, 0, 1, 5. Okay. And this says, is that a 5?
Yeah.
Yeah.
That's a 5. That was a 5.
Okay, so then this is a 3, 0. Very good. So this matrix is indeed in the fiber. So now all we need to know is that this matrix is a singular matrix. So does this have rank 2?
Well, I mean, if you have this thing.
What's the rank of this matrix?
Probably not right, actually.
Okay. So if this matrix if the determinant were 0, we would have a solution. But we can check. You're not so convinced? No. Okay. Yeah. I don't see it right now, but unless you have a reason that this is a singular matrix, and maybe it's not. Any other suggestions? Well, I think maybe people are a little tired and hungry for lunch, so why don't I write down my solution, and then you can think about it some more. And then when we come back later this afternoon, we'll discuss a little bit more how to draw the tropical determinant, and maybe we can even find a copy of this picture in our book. So here's a solution. Check me, So take t cubed and 1, and then we take minus 1 plus t cubed, t to the 5th. Okay, so this I think is okay on the first 2 columns. And now we take the first column plus t times the second column. Okay, so I'm going to make a linear combination. So I'm going to take this column plus t times that column. Gives me t to the 4th, t squared plus t cubed. Okay. So now this matrix has determinant 0, right, because the last column is a linear combination of the first 2 columns, and I think it has the correct valuation. Okay. So that's the content of the fundamental theorem. The fundamental theorem says if you have any point on any tropical variety, you can lift it. And there's actually lots and lots of lifts. Okay, and we'll see more examples. So why don't we take a lunch break now, and we'll reconvene at 1 o'clock for some questions and discussion about this morning's lectures, and including a discussion how to draw the Newton polytope and the tropical hypersurface of a 3 by 3 determinant.